So today we are picking up the problem of balancing of several masses rotating in different planes. It is known as dynamic balancing problem also. Now what is here? There is a shaft and number of masses are rotating at different planes. A1, A2, A3 and A4 are different planes. The masses rotating are M1, M2, M3 and M4. Their radial distances R1, R2, R3, R4 they are given here. R1, R2 is R1 is 0.27, R2 is 0.21, R3 is 0.3, R4 is 0.36. Thetas are also given. M1 is taken as theta is equal to 0. M2 is at theta 2 is equal to 45, theta 3 is 120 and theta 4 is 255 if it is measured with respect to x-axis. Now we know that when we are supposed to balance the masses in different planes, then we cannot balance it by single plane. We have to implement two masses in two different planes. The location of these planes and their radial distances are already given in the problem. So the plane is at L and M. Their distance from first A1 is given, that is all mentioned here, and the radius of balancing masses, that is the radial distance, is also given. Now how to solve it graphically, that we wish to discuss. So first of all we'll make the table. The table will have components like plane, mass, radial distance, centrifugal force divided by omega square will give us the term mr. Then L is the distance of a plane from reference plane. Now we are supposed to select either of the plane where we should implement the mass, that is L or M, as a reference plane. That is what we have picked up here. If you'll see, the reference plane L is taken as a reference plane. Now if we'll see the what are the components of this table. So plane number A1, we are having mass of 200, that is M1 is 200. It is at R1, the distance is 0.25. Then we have multiplied these two to obtain mr. Now we'll see the location of this plane A1 with respect to reference plane L. So it is 120 towards this side. So before this, that is towards the left, it is taken as negative, and towards the right of reference plane it is taken as positive distance. So A1 will be at minus 0.12 meter, that is 120 mm, and we multiply, then MRL will get this value MRL, that is the couple. So similarly, when we'll talk about plane L, balance to be implemented, balancing mass is ML, which is unknown, radial distance is 0.72 already given in the problem, so the force become 0.72 ml, and because the plane is distance of plane L from plane L is 0, so L is 0, so couple will become 0. A2 is 300, radial distance is 0.21 R2, then it is centrifugal force multiplying this, then radial, then distance location from the reference plane is 150, that is 0.15. We have got MRL. Similarly, we have calculated for A3, M and A4, that is all we have calculated. Now how to proceed further? If you'll see this couple, in the column of couple we have one unknown 0.36 mm, and in the force column we have two unknowns. So it is recommended to start the solution of problem will come from the couples polygon. So we'll make the couple polygon first, and after making the couple polygon we'll make the force polygon. So couple polygon is shown here, it is here. So what we have done, first of all we have drawn the first minus 6.48. So it is interesting how to take minus. Now this direction it is at 45, this direction is positive, so if I am taking negative, arrowhead should be towards the horizon. So that is what I have taken a suitable scale, and we have started the diagram from here. We have made minus 6.48 like this, it is negative. Positive would have been in this direction, so this is negative. Then where this finishes, I'll start the next couple, that is 9.45. So 9.45 it is going to be parallel to M2, this is this, so this is what we have drawn. Then After this we'll go to 21.6. It is parallel to M direction of M3, that is 21.6. Then M4, parallel to M4 we have 56.16. This is drawn like this. Now this is the last point, this is the first point, and we know that this all is going to make a closed polygon for the balancing. So the closing side, if I join the last point with the initial point, that will give me the value of unknown side, that is 0.36 mm. So I'll measure this 0.36 mm and convert it as per my scale, and I can show that the value of mm is going to be 106 kg. An angle can also be obtained. You can measure the angle with respect to this 0 axis, or you can measure from here also what is going to be angle. Normally in books it is given from this x-axis, so we can measure it from this direction. After making this diagram, we'll go for the force polygon. Now how to make the force polygon? We'll start similarly. We'll start with first one, 54. That is now positive, so it will be in the direction of this. So this is taken as positive 54. Then after that we'll have 63. So this is unknown. We'll keep it for the last side. Keep as the last side. So we'll take this one, 63. So it is in along the direction of M2. This is like this. Then 72, that is A3 direction, so it is parallel to this. Then 93.6 parallel to A4, all positive. Then after this we have obtained the value of mm. So as we have obtained the value of mm, we know that what is going to be 0.72 into mm, that is going to be 76.32. So we'll make 76.32 like this. It is parallel to what we have obtained from here, and magnitude is 76.32. When we'll get the last point, we know the first point, join them to get the value of unknown side 0.72 ml, because this is making again a closed polygon. So if we'll measure it, we can calculate the value of ml. It is going to be 161, and angle can also be measured directly from here with the graphical method. So this is how we can solve problem of several masses in different planes, and this method is applicable and easy for many kind of problem can be solved out of it. So this is the fundamental of dynamic balancing through graphical method, and this is the method how you can solve any kind of the problem of the masses in different planes. We'll proceed in the next lecture for the different problem. Thank you.